Hello everyone, my name is Konstantin Taranov and today I'd like to present our RDMA-enabled remote memory system that supports compaction that does not compromise remote direct memory access. First of all, I'd like to talk about memory fragmentation. Memory fragmentation is an old problem and any database system is prone to memory fragmentation. To explain memory fragmentation, the problem of memory fragmentation, I'd like to show you this abstract example. Let's imagine we have the following memory layout where we have some squares occupied and some of the free. And as you can see, the memory layout is quite sparse. And then if we imagine the case that the client wants to allocate a contiguous region of 5 squares, it would fail as there is no uh, contiguous region which would satisfy this request. That's why systems employ strategies such as memory compactions for compacting the memory, which would free up memory for satisfying such requests. As you can see, since the system managed to compact all the occupied squares to the left, now it has a contiguous region of 5 squares to satisfy client request. Actually, memory fragmentation has a negative effect on the systems as it wastes DRAM. And it was reported by previous researchers that for certain workloads, up to 40% of DRAM can be wasted. So system just cannot use it up to 40% of DRAM it could potentially use. When we talk about memory compaction, we first look at which language it's implemented. So we have managed and unmanaged languages. Where managed languages, they offers you automatic memory management, which performs compaction for you. Or you could implement the same thing in unmanaged languages and do compaction yourself. But regardless in what language your memory compaction is implemented, the systems rely on the same mechanism, which we called the use of indirection tables. The key idea of indirection tables is that the clients, they don't have direct access to the memory, and they hold so-called the key for accessing the object. And to find to get access to the objects, they first look up the object's location in the index, and then they find the actual memory address of the object. As systems use these indirection tables, they could freely move objects in memory. They could just move objects to different address in the memory and fix the pointer in the index, which doesn't affect clients which stores the key. However, in the recent years, we have seen huge explosion in the use of network accelerators such as remote direct memory access. On the slide, you can see recent papers or like recent systems which exploited RDMA for its low latency, high bandwidth, and lower CPU utilization. Unfortunately, this system, they bring higher performance, but they put some limitations in the design, in the system design. And the main limitation of RDMA that clients should have direct access to the virtual addresses of the objects. So in this particular case, clients holds a virtual address as a key, and then it directly accesses the memory. As you can see in this scenario, we don't have indirection table. And as a result, systems which employs RDMA with one-sided operations, they're not able to support compaction. What is more, when we implemented our first prototype, we benchmark what is the effect fragmentation has on the RDMA accesses. On the figure, you could see the throughput of one-sided RDMA reads, and for highly fragmented memory, we saw 20% performance drop for certain ZipF skewness parameters. That's why we designed CoRM. CoRM is our remote memory system that supports one-sided RDMA reads, and also it supports compactions. Clients can access the objects with one-sided RDMA reads, and their reads would be consistent, and our compaction strategy is RDMA safe. So the clients are not affected, and clients can still use the pointers that they hold. On the bottom of the slide, you could see API offered by CoRM. So clients can allocate remote memory and then work with this using free read and write calls. In our API, we distinguish between RPC-based reads, which is just read request, and the direct read, which is implemented using one-sided RDMA read operation. I will not explain all the details of our memory compaction strategy, so I'd like to invite you to read the paper, and here I'd like just to give you a brief intuition on our compaction strategy. Our compaction strategy defines blocks of the same type. By the same time, we mean that they store objects of the same size, and the block stores the same number of objects. In particular case, we have two blocks which stores 10 objects. So it finds two candidate blocks for compaction, and then it copies objects from one block to the corresponding slots in the second block. Then it remaps virtual address of the first block to the second block and deallocate the first block. As you can see, we reduce the usage of our physical memory, but we still have the same usage of our virtual memory, which means that both pointers are valid. So if a client holds the previous pointer, it could still access its objects as they stored at the same offset in the new block. The same strategy was previously proposed by Mesh. So we actually designed the same strategy independent from them. But anyway, I'd like to invite to read the paper. It's a great paper, and it has really good analysis. But here I'd like to focus on the difference between our strategy and CoRM strategy. So as we need to, as Mesh requires the object to be stored at the same offset, if we have a conflict in the offsets, such blocks cannot be compacted. So the mesh memory allocator would fail to compact such blocks. In our case, CoRM can actually compact the blocks, and then it would just put the conflicting object at a different offset. And we would call the pointer to such object as lost direct pointer. By lost, we mean that the client cannot directly access the object, but it can still find it and access it. And on the next slide, I will explain how CoRM achieves this. So the key idea or key concept of the CoRM, that CoRM assigns special unique IDs to each object. So each object is not uniquely defined by its virtual address, but by a combination of the address of the block and the object ID. Object ID is a randomly generated ID of the object, which is unique only within this block. So in the example of the block 2 on the right side, we know the address of the block, which is defined by the 1235AA. And then we have object IDs like 35. So that's how we could uniquely define this object number 35 in the block. Also, our address has a second part, which is volatile, which has offset hint. Of course, finding object in the block is not efficient. That's why the address, which is held by client, has a hint, which is the offset to the position where object is supposed to be. And the clients, they optimistically access the objects at the provided offset. Each time they access the object, they perform a simple object ID check. So we embed the object ID in the header of the objects, and the clients, after accessing it, they could verify whether they read correct object. For objects for which the client had wrong offset hint, we would need to perform pointer correction, which I would explain on the next slide. But here I'd like to focus whether this actually additional ID check can affect performance. Of course, if we compare with pure load store instruction, which are performed by memcopy, then we would have a problem. We would see a performance drop. However, our target is remote memory systems like farm, which already perform some checks for consistency. And if we compare with pure farm, there is no significant difference between CoRM and farm, as we just add one additional if check in the process. So previously mesh could not compact two blocks, but farm does, and it introduces these lost direct pointers. But as you could already notice that if mesh suffers from the problem in conflicts in the offset IDs, CoRM suffers from conflicts in the object IDs. So if we have two blocks and they have a conflicting object IDs, then we cannot compact, as object IDs must be unique within a block. We performed theoretical analysis and we found out that conflict in object IDs is much less probable than conflict in the offsets. So on the plot, you can see probability of compacting two objects given its occupancy. And as you can see in all cases, objects in CoRM, blocks in CoRM were more likely to be compactable compared to mesh. And the main reason for that CoRM can support different object ID sizes that could allow it to boost compaction probability. But anyway, for the particular examples, CoRM of 8-bit overperform mesh in terms of compaction probabilities. What is more, you could see that mesh was really great only at compacting low occupancy blocks. So if we have blocks which has just few objects in them, whereas with CoRM we could even compact blocks with 50% occupancy, which means if we compact two blocks with 50% occupancy, we would get a fully we would get a full block. So, and then by using IDs of 16-bit, we would have almost 100% probability of compacting such objects, which means that CoRM supports more aggressive compaction strategy than mesh, but by introducing this lost direct pointers. CoRM supports different strategies for fixing these lost pointers, and overall we call this process pointer correction. First, I'd like to talk about RPC calls. So all RPC calls, they implicitly fix this hint, so they fix the pointers implicitly. Client doesn't need to ask this. When you send RPC request to CoRM, it would try to access the object using its address and then checks the object ID. If it doesn't match, it would perform pointer correction. So pointer correction is finding new offset of the object within the block. For that, CoRM offers two strategies. First strategy is to rely on the metadata stored in the memory allocators. So we could actually store some volatile data which would map object ID to offsets. But this metadata is only accessible by a local thread. The second strategy is actually just directly scan the whole memory block and find it in a linear time. When we talk about RDMA, unfortunately, RDMA request can fail, as we would read an object and the client would perform an ID check and find out that it's rather wrong object. To solve such issue, clients can clients have two options. The first option is to issue an RPC read, which would fix the pointer, and then the client could continue using RPC read for a given address. And the second strategy is to use scan read. So by scan read, we call an operation when the client reads the whole block using one-sided RDMA and then locally searches for requested object. So as you can see, almost all API calls of CoRM, they perform pointer correction, whereas only one-sided RDMA read can fail. We performed the performance analysis of two approaches when we use the spread local metadata and scan memory blocks. I invite you to read the whole experiment in the paper, but here I'd like just to focus on key aspects. For the RPC, for one of the strategies, we had this unavailability period of almost 1 second, as we couldn't access metadata of the thread as it was busy with the compaction. But nonetheless, during the region after, we saw like really small drop in performance of 1%. For the second strategy, we did not actually notice any performance difference after compaction. If we talk about RDMA reads, we saw in the first strategy, when we relied on issuing scan read after a failed RDMA read, we saw a drop of 5%. And for the second strategy, when we were relying on sending RPC read, we saw a drop of 7%, which was only during a short period of time, as we as a client just need to fix pointer once. And the main reason why we didn't see actually a huge performance drop is CoRM always tries to preserve offsets of compacted objects. It first tries to move objects at the same offset, and only for the objects which have conflicts, they would move them to the different offset. Actually, clients would be able, the developers which would use CoRM, they could actually tune these parameters and then prevent more than X lost indirect pointers in blocks after compaction. But in that case, we were just checking whether two blocks compactable. If they're compactable, we would always compact, even if it creates many lost indirect. It creates many lost pointers. Now I'd like to invite to read you the full paper, when we actually also explain how we preserve RDMA accesses by updating the translation table in the network controllers. Also, we explain the problem of virtual address exhaustion and how we addressed it. And then we perform detailed comparison between core, mesh, and farm, and explain all the overhead of CoRM compared to mesh. Finally, we provide additional experiments when we check the compaction property of CoRM in real settings for Redis workloads and for synthetic workloads. Thank you for your time. If you have questions, you can contact me through the email you can see on the screen. Also, you could download CoRM and try it yourself using the link to the GitHub.